So let's look at B. The nice thing about B is we can use, we got to pay attention and make sure that we notice that we're approaching 1 now instead of negative 2. So if they're doing multiple limits in this type of problem, you got to be careful. But we could split this using law number 4 into the limit as x approaches 1 of f of x times the limit as x approaches 1 of g of x. So what is f approaching as x approaches 1? Two. Okay, and what is g approaching as x approaches 1? Eric's got the hand symbols going, but I can't tell what he's saying. Negative 2? Well, that depends. Did you say negative 2, Eric? Yeah, well, as we approach from the left, it's approaching negative 2. What is it approaching as we approach from the right? Negative 1. So does that limit actually exist? No. Okay, since it's approaching different values from both sides, that limit doesn't exist. So first of all, I'm going to write a little DNE in here, does not exist. Okay? And then I'm going to refer you back a little further in the notes. Because in the notes, up at the top, it said, suppose that C is a constant and the limits exist. So if the limits don't exist, then we can't apply this step at all. And so this just is essentially undefined. So we would write, just for our answer, we would write it doesn't exist, because if one of them doesn't exist, then that whole limit doesn't exist. So that's our answer for that one. The limit as x approaches 1 of f of x times g of x does not exist. Okay. Does not exist. All right, let's look at C. The limit as x approaches 2 of f of x over g of x. Now, we might have to approximate here. So first of all, let's split this using law 5 into the limit as x approaches 2 of f of x over the limit as x approaches 2 of g of x. Now, we should be able to look at this and say, okay, I'm going to have to approximate for f. That's not so bad. But I'm going to have a problem when I look at g. What's my problem? What is the limit as x approaches 2 of g of x? 0. And so, regardless of what I estimate my numerator to be, maybe 1.4-ish, my denominator is 0, which is undefined. And so this violates another law, another condition from our laws, that the limit of g of x not be 0. So this is also a does not exist limit. Can't find the limit at that point. Any questions on example 1? I know I ran through it fast, that's why I asked you to read ahead. Okay. So, as we progress through the book there, you'll notice that we come upon rules 6, 7, and 8. There are proofs for these. I believe they're in the back of the book in Appendix E. I'm not going to walk through them in detail, but they do in the back of the book in case you're wondering where they come from. But we can get Law 6 by applying Law 4 over and over again, because Law 4 is the product rule. If we apply the product rule to itself over and over again, we get an exponent law. Okay? So the limit as x approaches a of f of x to the n is equal to the limit to the n power. So you can pull that exponent out. 7 and 8 are really important. They're actually ones you would almost prove first before you would prove the others. They're fundamental, and they're used to prove the others. The first one is that the limit as x approaches a of c equals c. Now that one seems a little weird because it doesn't involve x or a, but that's exactly why it's c. Okay? There's no x that we're putting values near a into. There's just a c value. Imagine a constant function like y equals 4. No matter where you are on that graph, your output is going to be 4. Your limit's always going to be approaching 4. Okay? So the limit of a constant function is just that constant. The limit as x approaches a of x equals a. Okay, that's just the line where y equals x. So you're always approaching whatever x value you're at. And then if we combine those two laws, we combine laws 6 and 8, we get the limit as x approaches a of x to the n is equal to a to the n, where n is a positive integer. Now we'll prove later, or at least we'll use and state later, that n doesn't have to be a positive integer. It doesn't have to be that limited. But for where we're at right now, n is a positive integer. And this is very helpful because that covers basically all of your power functions. And when we put that together with the sum law and the constant multiplier law, we're going to find something real handy for polynomials here shortly. Laws 10 and 11. 10 is very similar with roots where n is a positive integer. So the square root, the cube root, the fourth root, fifth root, and so on. We can essentially plug a right in. And the same is true if we have a function under there. If we're taking the limit of the nth root of a function, it's equal to the nth root of the limit of the function. And we're going to assume that function is greater than 0 if n is even, because you can't take the square root or the fourth root or the sixth root of a negative number. So that's why we're assuming that caveat that f of x is positive. So we use all of these laws to apply an example 2. Basically what we do is we take and break them down piece by piece and evaluate each of the individual limits. Now I'm going to skip A. I'm going to do B because it's slightly more involved and it covers the same steps we'd use in A. The only difference with B is that it has a denominator, so we've got to do a little more work. And so the first thing we would do is apply Law 5, which says we would take the limit as x approaches -2 of the numerator and divide it by the limit as x approaches -2 of the denominator. Okay, that's law number 5, where we split according to the quotient. And then we could use our sum rules and our difference rules, law 1 and 2, to split this up into the limit as x approaches -2. I'm going to use a copy and paste here because this takes forever to write. Of x cubed plus the limit as x approaches -2 of 2x squared minus the limit as x approaches -2 of 1 over the limit as x approaches -2 of 5 minus the limit as x approaches -2 of 3x. So we're taking all the individual pieces. And then we can look at all the different laws we have and see how they apply. This is a law 9 situation. We've got x to a power. This is a combination of laws 3 and 9, because we have that coefficient of 2 and then that power. Okay? This is a law 7 because we're taking the limit of a constant. This is a law 7 because we're taking the limit of a constant. And this is law 3 because we're taking the limit of a number times x. And then also we could use the limit 8. Okay, so law 9 says that when I have x to some power, where that power is a positive integer, I can just plug in -2 for x. And so I'll have -2 cubed. Let's use a different color here. Okay, law 3 says I can bring that 2 out front, and then law 9 says I can plug the -2 in and raise it to the power. And law 7 says that the limit of a constant is just equal to that constant. Same for the first step in the denominator. And then law 3 says I can bring that 3 out front. And law 8 says I could plug in -2 for that x. And so we have -8 plus 8 minus 1 over 5 plus 6, which is equal to -1/11. Notice that the bottom is not 0. That's important because we used our quotient property. And that all of those limits existed. We didn't have any weird limits in there. Now, the ironic thing about this problem is if I had just given you f of x equals x cubed plus 2x squared minus 1 over 5 minus 3x, and I asked you to evaluate f of -2, this is exactly what you would have come up with. Which is kind of annoying, I think, because it makes you go, well, why can't we just take a step back to Algebra 2 and do what we were doing before? Because we're looking at these functions more in depth, and we're saying, well, what happens if your function isn't defined there? What happens if it's defined around there? And those are the problems that we're going to address as we move on. We're setting a foundation right now for how to approach these problems and find where our issues occur. And what happens when our laws that we've learned don't apply, which is what we're going to see as we turn on to page 107 as we move along in the notes. So are there any questions about this problem that we covered so far? Okay. We'll find later on that with polynomials and rational functions, like these two examples, really you can plug in the number. Okay, and you're not going to be in much trouble as long as your denominator's not 0. So we'll get to why we can do that here in a second. Oh, right now, actually. The direct substitution property. One of the few with a special name. If f is a polynomial or a rational function and a is in the domain of f, that's the kicker. A has to be in the domain of f. Then the limit as x approaches a of f of x equals f of a. So basically we have to make sure that your function is defined when x equals a. Now for a polynomial function, unless you've got some weird contextual issue going on, polynomial functions are defined over all the real numbers. And so you can always use direct substitution. With a rational function, all you have to really make sure is that you don't have a 0 in the denominator when you plug in that number. That's when a is not in the domain. So in this last problem that we did, the only number not in the domain of b is the only number not in the domain of the problem in b is when 5 minus 3x equals 0, which is x equals 5/3. That's the only number that we couldn't use direct substitution with because that's the only number not in the domain. Okay? We'd have a 0 in the denominator. Our functions... our function's not defined there, and so we have to be careful around that point. Otherwise, we can just plug the number in and see what we get out. Any questions on that? Okay, so we have to be careful because direct substitution doesn't always work. And so the times when it doesn't work are exactly what's stated in its qualifier there. A has to be in the domain of F. So if we look at example 3, and we look at this function, is this A value, is 1 in the domain of this function?
No.
Why not?
You can't divide by 0.
Because if I plug in a 1, I'll have a 0 in the denominator, and I can't divide by 0. So I can't just substitute in 1. Now, the good news is, we're not completely lost. There is a technique for evaluating this limit. We're going to use it, and then we're going to define it. So if you notice, the numerator is factorable. Okay, we discussed this when we were discussing rational functions in pre-calculus, that sometimes you can eliminate a factor in the top and the bottom. What does the numerator factor into? X plus 1, x minus 1. It's a simple difference of perfect squares. And so we'll see our numerator and our denominator have a factor in common that we can cancel out. And so we suspect, we haven't stated this specifically yet, but we suspect that this should be the same as the limit as x approaches 1 of x plus 1. Now remember that when we had this type of situation in pre-calculus, and we had a common factor in the numerator and the denominator, we said that instead of having an asymptote there, our graph has a hole. Okay, it has this open space that it's approaching from both sides. And as we've seen in calculus so far, when that happens, our limit is still defined because it's still approaching the same number on both sides. And the function is defined near that hole, even though it's not defined at that point. So it seems intuitive. And if this is the case, if this is true, then now we have a polynomial, and by our direct substitution property, I can evaluate that simply by plugging in 1 for x and getting 2 out. And you'll find that that is the case if you graph that on your calculator. This is basically going to look like a line, x plus 1, but it's going to be undefined at that specific point when x equals 1. So we computed the limit by substituting in a different function. We replaced the function f of x with g of x. G of x being x plus 1. And the reason we can say they have the same limit is because f of x equals g of x except when x equals 1. And when we were first defining limits and saying what we could and couldn't do with them, we were talking about what's happening near 1 except, and so our function has to be defined near 1, but not necessarily at exactly 1. And so since f and g are equal everywhere except for at 1, then their limit at 1 is still the same. And so, sorry, was somebody saying something? All right. Sometimes I hear things. And so we can state that if f of x equals g of x when x doesn't equal a, so everywhere but that one point that you're looking at, then their limits are equal as long as their limits exist. It seems really, what's the word I'm looking for? Unnecessary. It seems just kind of extra, but it's extremely important because it's what allows us to simplify and rewrite functions that we normally wouldn't be able to find the limit to, and now find the limit of them. And so this is actually one of the most important rules that we have for calculating limits. The other ones are what allow us to walk through the algebra, and those are easy to remember. This is what allows us to rewrite an entire equation into a basically equivalent equation and calculate its limit. Any questions yet? Okay. So we have this related problem. Now, imagine if I were to graph this type of problem, okay? If I were to graph this equation, it would look really weird, first of all, okay? And I'm just going to do a rough sketch. We'd have some line with a y-intercept of 1, but there's a hole at x equals 1. Okay? And at that point, instead of it being equal to 2 or whatever our line would normally equal, it equals pi. Okay? This is basically what that function would look like if I graphed it. If this is 2, this is 1, this is 3, and this is pi. That's basically what it would look like. And we already evaluated issues like this with limits. And we said, okay, I don't care what this point is. I don't care what's happening at x equals 1. I care what's happening near x equals 1. Okay? I care what it's approaching. And so we already looked at this with graphs last week and said, well, of course, that's still going to be 2. Who cares what's happening at 1? We care what's happening near 1. But what that last property says is that the limit as x approaches 1 of g of x is equal to the limit as x approaches 1 of new function x plus 1. Because g of x and x plus 1 are equivalent functions except for at that one point, except for at this value right here. And since that's their only difference, their limits there are going to be the same. So what we're doing is we're using this concept to basically remove little irregularities in our graph. And we want to evaluate again. This is one of the most important concepts you can get into your head, is that the limits are evaluating what's happening near that point, not necessarily at that point. What's happening near 1, not necessarily at 1. Does that make sense? Okay. So moving along, the rest of this lesson covers a lot of usages of these laws. So we want to evaluate the limit as h approaches 0 of 3 plus h squared minus 9 over h. Now, the reason we can't directly substitute 0 in, we can't use the direct substitution property, is that 0 is not a part of that domain. That function is not defined when h equals 0 because we'd have a 0 in the denominator. So we have to use a different approach. We want to simplify the function. Basically, what we're looking for is a way to remove that h from the denominator. And so the best strategy with this setup is to figure out what our numerator actually looks like if I multiply that out. So just a quick check of Algebra 2 skills, actually Algebra 1 skills, what do we get when we square 3 plus h? H squared plus 6h plus 9. Okay? Some of us on our test are still writing 9 plus h squared. Don't forget that you have to multiply this out as 3 plus h times 3 plus h. Okay? When you just square the 3 and just square the h, first of all, that's not a property of exponents we're allowed to apply. And second of all, you're missing a couple of important terms. And so we do get, depending on what order you write it in, if you multiply it directly like that and don't reorder things, you'd probably get 9 plus 6h plus h squared. Not that the other way around is wrong, just rearranged. All right, so what is the top simplified to? That should be fairly easy. H squared plus 6h. And now we should notice that in the numerator we can factor out an h. This should look a lot like a problem you did on your pre-calculus final. There was one very similar to it on your pre-calculus final. It was setting you up for calculus. If we factor out an h on the top, we can use it to eliminate that h on the bottom. And so we can rewrite this function as the limit as h approaches 0. Instead of using that whole rational function, we can just use h plus 6. Or 6 plus h, however you want to write it. So I want to restate something here in terms of that last rule that we looked at. That last outlined box in your notes. Okay? H plus 6 is equal to 3 plus h squared minus 9 over h for every h value except 0. Those two functions are equivalent at every point except for when h equals 0. And so since I'm evaluating their limit at h equals 0, I can use either one because they're equivalent at every other point. And so I choose to use the one that is defined at 0 because that just makes sense. And so since that's now a polynomial function, it's a very simple polynomial function, I can use the direct substitution property and say that's equal to 0 plus 6, or just 6. Does that make sense? Are there any questions on that one? All right. If I'm going too fast, let me know. If I'm going too slow, you can let me know. I'll probably still go slow. At least while I'm recording today. If everybody was here, that'd be different. I'd maybe speed along. So let's look at a problem that we saw in the last section. It was a really weird looking equation. This just highlights the same thing. That is the same problem that's the difference quotient for x squared at x equals 3. That's the setup we would have used to calculate the slope of the line tangent to the equation f of x equals x squared at x equals 3. And so h would be the distance between the arbitrary x values near 3 and 3. So it'd be some value near 3 minus 3. And by calculating the slopes of the lines connecting the points 3, 9, and some x value, and choosing successive x values approaching 3, we can determine the slope of the tangent line at x equals 3. We will get to that more in depth later. But the important thing is that this is going to tie all the way back to what we learned at the beginning of the chapter, the tangent line at a point. But let's look at this example, which is one that we covered in 2.2. This is the one that had the really weird calculator issues. Because we were trying to evaluate for t at 0, and so we used points near 0. And the closer we got to 0, the harder time our calculator had seeing the difference between t squared, the square root of t squared plus 9, and negative 3. And so we suspected when we used larger values of t that would be equal to 1/6. But when we got closer and closer to 0, our calculator made it appear that it was approaching 0 instead of 1/6. So we're going to use the algebraic approach here to see what we would, what it really is. Now, here's the weird part. Looking at this, we don't have something that we can FOIL out or distribute out in the numerator and cancel out with a t squared. We don't have a radical in the denominator rationalize. And we've got a t squared in the denominator that we can't plug 0 in for. So we have to use a really strange approach, at least in my book, to rewriting this equation. And so what we're going to do is we're going to take and multiply this. I'm going to write it out in more detail than the book does because I want you to understand why this is valid, why we're allowed to do this. So the first thing I'm going to do, this is going to look really weird. It's going to look useless until you see how it all fits together. I'm going to multiply this by the limit as t approaches 0 of 1. Okay? Now, first of all, the reason I know I can do that is because the limit as t approaches 0 of 1 is 1. Because the limit of any constant function is that constant value. That's law number 7. But then what I'm going to do is I'm going to rewrite that value of 1 in a different format. This is where it gets super weird. These steps aren't entirely necessary for the work. I'm just trying to demonstrate in great detail why we're allowed to do what we're doing. So don't feel like these are all the steps you need to take when you're doing this problem in your homework. So what I'm going to do, instead of using 1, I'm going to use a different function that equals 1. And that function is the square root of t squared plus 9 plus 3 over the square root of t squared plus 9 plus 3. So first of all, this was allowed by law 4 because law 4 says that equals 1, and I can multiply anything by 1. And then I don't have a number on this law, but if let's back this up, if f of x equals g of x, then the limit of f of x equals g of x equals the limit of g of x. So I have that one box that says I can replace one function with another. Now I didn't put any actual t approaching thing underneath there, so try not to shoot me for that. But since because this function equals 1, the limit of that function equals the limit of 1. That was that weird box that we had in between example 3 and 4. And then I can use law of 4 again in reverse to say this equals the limit as t approaches 0 of the square root of t squared plus 9 minus 3 over t squared times the square root of t squared plus 9 plus 3 over the square root of t squared plus 9 plus 3. So let me just restate, because sometimes it gets lost or misunderstood. You can start right here when you're doing this problem. That's an okay place to start. I wanted to show you all the steps that made that legal. I didn't often have a professor that did that for me. They said, oh, they just said you could do this. Well, why can you do this? So now our tactic is going to be to multiply out the top and bottom. Now, I'm not going to go into a lot of detail about why these equal what they equal. And I'm not going to distribute through the bottom. I'm going to leave it factored. So let me write the bottom first. Now the top is a little bit weird, but when you actually multiply it out, it's very simple. If you'll notice, if you call this piece A and this piece B, then you have a difference of squares. And so when you multiply that out, you get A squared minus B squared. And in this case, A squared is just t squared plus 9. It would cancel out that radical. And you got minus b squared, and b is 3, so b squared is 9. If you want to do that out, distribute that out rigorously yourself, you can. But here's where the simplification comes in. The top is going to simplify to t squared. Because those 9s will eliminate each other. And then that t squared in the numerator is going to cancel out with the t squared in the denominator and leave you with the limit as t approaches 0 of 1 over the square root of t squared plus 9 plus 3. And so through all these steps, we should recognize that this function is equal to the original function everywhere except at t equals 0. That's the only point where they're not the same. And so since that's the only point where they're not the same, then the limits at that point are equal. And now I have this really weird function, and we have to be careful about using our direct substitution property. First of all, what type of functions does our direct substitution property apply to? It's there in your notes. For what type of functions can we use the direct substitution property?
irrational.
Polynomial or rational functions. Thank you, Caleb. Now, this clearly isn't a polynomial function, but where we might get tripped up is when we ask ourselves if it's a rational function. And is it a rational function? It's actually a pre-calculus question. Is it a rational function? Now, since I'm asking the question, you probably would assume that it's no, but you want to say yes because it's a fraction, and fractions are ratios. So why is it not a rational function? And if we remember from pre-calculus, what defines a rational function is that the numerator and the denominator are both polynomials. And that denominator is not a polynomial because it has that radical in it. So this is technically not a rational function. So we have to be careful about just saying, well, now I could plug in 0. You can't plug in 0 because the direct substitution property doesn't actually apply to this problem. Now, that doesn't mean we're done, as much as you might like to be. That doesn't mean we're done. It just means we have to be a little more careful about how we approach calculating this limit. So I'm going to get a little more room on the page here. I'm going to rewrite the conclusion that we came to, and I'm going to show you how we'd evaluate this limit piece by piece. And this is where we'll close for the day. Now, first of all, with our quotient property with law 5, we know that we can take the limit of the top over the limit of the bottom. Okay, and we know that the limit of the top is just 1. That's law 7. We can split the bottom into the limit of the individual pieces. And the limit of 3 is just 3. So I'm combining their law 1 and law 7. So law 1 let me split the sum, and law 7 said that the limit of 3 is 3. But now we're taking the limit as t approaches 0 of a radical, and that's not a polynomial or rational function, but we do have a law that covers that. The law that covers that is law number 10. Sorry, not 10. I'm wrong. 11. Which says I can push that limit underneath the radical, or pull the radical out over the limit if that's the way you want to approach it. And now I have this. Okay, so that is law 11. That's not the Super Bowl, that's law number 11. Okay. And now I'm taking the limit of a polynomial because t squared plus 9 is a polynomial. So now I can plug in 0. And so I get 1 over the square root of 9 plus 3, which is 1 over 6, which is what we suspected the limit to be. Are there any questions on that problem? All right, any questions on what we covered today? All right, so we will finish section 2.3 on Thursday. Make sure you're keeping up with your homework. And if you have any questions, feel free to email me. Look for a quiz showing up soon on WebAssign. And don't forget that there's no class next Friday. Other than that, you guys can have a great day. Thanks for showing up. My condolences to any Patriots fans. Not because the Patriots lost, because that I'm happy about. My condolences because you are a Patriots fan.